Yeah, we'll get started. So we have Sylwester here today. Maybe Claire will give a brief introduction.
Okay. Sylwester already prepared to introduce himself, but I'm super excited that he could be here in New York with us. So Sylwester is currently are you a professor? No, that's not officially your title.
No, I'm not a professor yet, definitely.
I think we would call it an assistant professor in the US.
Yeah. Post.
But they call it something else in Poland at the university in Krakow. And he is here right now visiting on his way to AMS next week. So very excited that he was able to come through New York. So Sylwester did his PhD at the University of Warsaw with Hanna Podlaska, and then went on to a brief break in finance, came back into the cloud world, did a postdoc where he started developing ISDM, which we just got to talk with him about. Then he went 2 years ago to University of Illinois, Urbana-Champaign, worked with Nicole Reamer's group, where he started working on what he's going to talk to us today about, which is aerosol modeling PyPartMC project. And now he is back in Poland, like I said, at the University of Krakow as an assistant professor. And Sylwester has a lot of expertise in cloud microphysics, aerosol cloud modeling, and also software development. So he writes very beautiful code, which I've had the pleasure to work with, and hopefully some people here will soon be working with as well. So yeah, we're really excited to have Sylwester and very excited to hear about his talk today about PyPartMC.
Thank you. Thank you for the opportunity to present and to brainstorm with you. Let me just ask, where's the camera? So
Right.
this one. Okay. So the topic of my today's talk would be PyPartMC Aerosol Dynamics package. But let me be fair and put the subtitle, which I suggested to be Engineering Python-to-Fortran Bindings in C++ for use in Julia and Matlab. So probably I was trying to stick as much as technologies as possible in one title. But to be fair, this talk is meant to focus on software engineering, but not in a very technical way, rather in a conceptual way, explaining how we manage to cope with a challenge that probably a lot of groups are facing, namely how to continue using legacy codes in a typical modern setting where users of our code expect it to be easily interoperable with all the cloud computing ecosystem, interpreted language ecosystem, etc. So let me also acknowledge the team for the PyPartMC project. So this was done during my postdoc at UIUC with Nicole Riemer and Matthew West. And let's say the coding work was led by me, but with very, very active contributions from Zachary Dakino and Jeff Curtis, as well as several PyPartMC contributors which joined us, leveraging the fact that this is an open source project. So let me start with the context and what was the need for creating the PyPartMC package. So PartMC, without the Pi prefix, is aerosol simulation software developed over the years at the group of Nicole Riemer and Matt West. It's the MC in the name stems from Monte Carlo approach, which is the key concept in the project. So it's open source and it dates back to almost, I would say, 20 years with a version 1 mature release in 2007, developed by the group at Urbana-Champaign. And in principle, it's a box model focused on aerosol physics and functional chemistry. However, the group at Illinois actually exemplified already how to couple it with multi-dimensional large-scale simulations, for example, with the coupling to WRF. From the physics point of view, it resolves coagulation of aerosol particles, condensation of vapor leading to cysteine activation, and gas and particle phase chemistry through the use of external packages, either the Mosaic from PNNL or the open source CAMP, that is a collaboration between University of Illinois, Barcelona Supercomputing Center, and the CART. And the highlight for the project in general and of the literature that uses the PartMC is aerosol mixing state evolution simulations, analysis, and insights into the detailed composition and mixing state of the aerosol. What is important from today's talk point of view is that even though I used already the word legacy software, I would say that this is a very best example of legacy software, because despite the 20 years of development, it's actually an object-oriented Fortran code base with extensive and automated test suite. So something that is a very good starting point when we think of extending it towards other technologies. And to paint a picture of the challenge that we faced and the goal was to answer this question. So how to bridge the PartMC world on the one end, with most of the code base written in Fortran, part of it in C, and several dependencies for the numerics, with the typical expectation of a user in nowadays scientific setting, meaning easy interoperability with the tools we use to analyze our data, to prepare input for our simulations, to visualize the output, to execute simulations on other computers, etc. And here the keyword is Python/Jupyter ecosystem. I think it nicely describes in one phrase what is this need. So these two worlds are apparently kind of, if not orthogonal, not truly interoperable. And this talk today will be about how to cope with it in a way that would not incur work that would be hard to maintain, and that would not incur the work that would lose the connection with the existing code base. So what are the goals and the status of the project? The goals were to lower the entry threshold for installing and setting up of PartMC. So actually, what we have identified as the key challenge for users of PartMC was not actually the physics or chemistry or running the simulations, not even analyzing the output, but actually getting it running. So for a student or for a group of students to get it running on their very diverse machines and diverse environments, it was somehow a challenge due to Fortran, due to compilers, due to multiple languages, the C and Fortran, due to the libraries, NetCDF, sundials, due to the constraints on the versions of libraries, and due to also the different operating systems. Linux, macOS, Windows, and then multiplied by the number of hardware options available. So we wanted to ensure that the same experiences for all those systems, and we also wanted to lower the entry threshold by providing examples of how to run simulations from a familiar Jupyter environment. And finally, a kind of a benchmark for us was to assure that we are able to disseminate simulation automation and simulation scripts to peer reviewers of our papers in a robust way, meaning that we can expect that the reviewer would be able to obtain it of easily from legal perspective and from a technical perspective, run it and obtain results that are provided in the paper. So this is the status of the project. I would say we delivered version 1.0 just last month after 2 years of development, and we have announced the release with a journal paper in the SoftwareX journal, and the packaged versions of PyPartMC are available as pip installable packages from the Python package index. And now let me move on to a brief outline of the design and the implementation. So essentially, maybe kind of counterintuitive, the starting point and the idea of how to cope with these challenges that I've outlined was the realization that we can actually use a framework that is aimed at interoperability between C++ and Python. So C++ is not a language that was part of PyPartMC code base. C++ is also not a native technology for Python. However, the object-oriented structure of the Fortran code base of PyPartMC was one of the reasons to look at it this way. Let me just mention that it's one of those packages that probably a lot of software developers admire, with more than 300 contributors, more than 2,000 forks on GitHub, and 14,000 stars. Well, it's probably subjective if it matters or not, but definitely it's a project that is very mature, widely used, and actually one of the big players behind its development is Google. So now how it fits. So essentially it fits in this here in between. So PyBind 11 is a way to automate creation of Python packages from C++ code base. So we have realized that the way to implement PyPartMC could actually be to develop C++ bindings to PartMC that would map the object-oriented structure of the package, and then let PyBind 11 to automatically expose these C++ things to Python. So essentially, the project actually has 0 lines of Python code. It's a Python package written in C++ to interface with Fortran. And it has many implications that I will outline. So C++ has the advantage of shared binary interface with C, which is also shared with Fortran. So C for us is a common denominator or common way of interfacing it. So actually what happened is we have first developed a C interface to PartMC with a kind of manual object orientation, and then a C++ layer over it. And then the C++ PyBind 11 tool automatically exposes it to Python. This implies that we are exposing PartMC internals, actually, not the user-facing way it was originally offered to users. So PartMC originally was a binary that one would use from a shell in Unix environment with command line options and input from files out to files. Here, we actually interface the internals of the package, allowing the users to do time stepping on their own, to interrogate all the objects on their own, to do their own initialization, and to also work instead of input or output files with their own data structures. The build automation is done with CMake and test automation with PyTest. So we are leveraging some of the technologies that are used outside of Fortran community, which is one of also achievements here, because the things like packaging, test automation, build automation are not the strongest points of Fortran. And here we managed to somehow encapsulate the Fortran written code base within the tools from other ecosystems that do it well. We have also embraced JSON as the key data layer for the whole project. And actually the way to do it was a bit tricky, because we assumed that early on, we assumed that we need to work with unmodified code of PartMC. So this is probably, if you imagine your favorite Fortran project, and you imagine that you might need a Python interface to it, I hope that it sounds like a good idea to make this Python bindings work on the original code, not on the modified code, just to make sure that further updates in the interfaced package are still not diverging from what we use. This was our assumption. And this implied that if we want to replace the input-output file logic of PartMC with something else, we need to write it in a way that actually PartMC doesn't know that it operates on in-memory structures, Python structures or JSON-like objects. But PartMC thinks still it uses text files, multitude of text files in a file system, but in reality, it uses JSON that is passed by the user. We have also managed to couple Fortran the allocation logic with the Python garbage collector, which was one of the challenges. And one technological, also probably maybe not achievement, but a solution that we came up was to pin all the dependencies of our code and their versions through Git submodules. So we are actually keeping in our Git repository of PyPartMC submodules linking to particular versions of all the dependencies, which are actually not the list of dependencies is not that short. So we have Fortran dependencies like PartMC, camp, netcdf Fortran interface, sundials. We have no sundials. This is probably we have C dependencies. We have C++ dependencies. All this together, more than 10 packages that we need to have at hand to compile PyPartMC, and we clearly do not want the user to obtain these things by herself or himself. We want it to be automated, and the way to automate it was to ship it through the Git submodules. So whenever someone clones the repository, it comes with all the versions there. And at the time of building and package dissemination, we actually statically link all these dependencies into one single file. So when someone gets PyPartMC Python package, it comes with all these dependencies statically precompiled into one single file. So installing PyPartMC by doing pip install PyPartMC means that what comes into the system Python package folder is a single file with all these dependencies inside. So one does not need to install PartMC, for example, to use PyPartMC. So this is all compiled in one single binary. So how it looks from a user perspective, sorry. This is first the original Fortran setting. So a lot of code, and I'm not intending to show the actual lines. Please treat it as a pictorial representation of the volume of code needed. And just please look at different components. So we have some Fortran code that drives a simple simulation here. And a set of 3 text files that contain a minimal input describing the aerosol state at the beginning of the simulation. So we have 2 modes, and these modes are composed of some here organic carbon fraction. So this is a very, very minimal, probably the most minimal setting. Usually the PartMC simulations imply an order of magnitude larger initial setting, but this is technically how it looks from a Fortran user perspective. What we have achieved is given here. So from Python perspective, we can now import PyPartMC and do the very same thing that the previous slide code does in a single file, single technology with all the specification of input as JSON-like structures in Python with PartMC that is compiled into PyPartMC, not actually knowing that something changed. So PartMC Fortran code still thinks that it operates on the original PartMC format input text file, while what is here is actually in-memory Python objects mimicking JSON and JSON serializable, JSON deserializable objects. Now the big thing that comes kind of for free when you develop Python bindings is that actually you can use the same package from other technologies. So here on the right, there is a Julia snippet, which does exactly the same. And actually all these Fortran, Python and Julia codes are part of our continuous integration setup. And we check if what is printed here matches across all the languages whenever someone proposes a change to the project. So you see that using it from Julia is literally the same from the conceptual workflow point of view as in Python. So also this conciseness of the code is achieved. Finally, the added value is also that not only open source technologies can interface Python, but for example, here there's an example of the PartMC simulation run from within Matlab using the Python interface that is built into Matlab. So now if a user comes to PartMC group with MATLAB experience, using PartMC boils down to, doesn't need to actually go out of MATLAB. We can use it without shell, without Python, without seeing Fortran, without seeing compilation, C, linking, etc. Leveraging that MATLAB has a built-in Python interface, which allows to import and use Python packages. So how it works in terms of workflow. So here at the top of this diagram, which is kind of control flow diagram, you see the three columns are C++ code, Python code, MATLAB code, Julia code, and here at the bottom C code and Fortran code. So unfortunately, there is a large mixture of technologies. But for example, if we take the Julia user perspective, we have Julia user code that uses the PyCoJL, a standard layer for interfacing Python. This communicates with this PyBind 11 generated Python module, which actually executes C++ code, which calls to the C layer above PartMC that we developed to access the Fortran layer, which accesses the original unmodified PartMC logic. This unmodified PartMC logic has calls to the CDF, CAMP for chemistry, Mosaic for chemistry, and to this spec file layer that does input-output, the input files and output. And we provided a drop-in replacement, kind of a mock of this, taking out through at the compilation stage the original spec file code from PartMC, replacing it with our own C++ written layer that uses C++ JSON library for interfacing the in-memory Python structures. Kind of convoluted thing for the development, but for the user, it looks like just sending Python dictionaries, lists, tuples to Fortran without much trouble. So Now, let me also mention that we have aimed at including in the C++ code base all the metadata for the API of PartMC to reflect what is also documented for the Fortran code, and it is publicly available on a auto-generated website from the code base. And maybe let me try what usually does not work during public presentations, but why not? So can I open Chrome here? Okay, so here we have the talk. Let me confirm if the virtual audience can see me clicking on GitHub.
Yep, we can.
Thank you. So I will now go to the PartMC GitHub repository where the development takes place. And in the README file that is displayed here, we are listing 4 main examples that we provide for our users to start experimenting with the package. So we have an urban plume scenario demonstration that is similar as the flagship example from PartMC. We have a dry wet particle size equilibration example, which compares the PyPartMC interfaced logic to PartMC, and another Python package that covers similar functionality. We have an example that covers processing of output and loading netcdf files with the netcdf logic for these files from PartMC Fortran code from Python. And we have an example that does time stepping of a simulation from Python instead of Fortran, and uses an external Python package to supplement the logic of PartMC simulation, in this example with me-scattering optical calculations. So maybe not sure which one to try with. So essentially here we have all these badges that are links that allow to open a given example in a public execution platform. So ARM Jupyter Hub requires authentication. Colab requires a Google account. So maybe let me try to launch a binder, which is anonymous. And okay, let's risk and let's try to open the most challenging one. So I'm opening in a new tab, and it's not my notebook, so I hope this will be a nice proof that it actually works anonymously. So I'll let it start and let me go back to the presentation. It was quick, actually. It was very quick. So here is the notebook running anonymously on the mybinder.org platform. And here is a set of model input and some simulation logic cells that should exemplify how to interface this me-scattering package, completely different Python package, with PartMC. So let me try running it. It seems to work. So let me run all the cells. I did expect it to work, but I expected it to be a bit slower. So let it run, and let me continue with the slides, and we'll come back to see if there is some plot available in a moment. Yes, this was the starting point for the demo. And so to summarize, and there is a bit of slides of summary, so it will take me a bit of time. So let me mention that actually there were some surprises. So for example, we have a few PyPartMC firsts. So actually using PartMC on Windows seemed never to have been even tried. And now this pip install works. So actually, I've learned a bit after coding it. So I assumed that it was the case that it should run, but after it started running, I was informed that actually no one ever tried earlier, as far as I understood. If we have in audience someone who did try PyPartMC on Windows, please correct me. A bigger surprise was that PyBind 11 for Fortran was actually also not ready to use the use case. And then even more, maybe not more surprising, but a more intriguing, in a way, technical intriguing thing was that when we tried to use the PyBind 11 generated packages from within MATLAB, despite PyBind 11 has all these thousands of stars, forks, and users, it actually did not work. So MATLAB was doing something fishy with the internals of how the shared objects, the DLLs, etc., are interfaced. But fortunately, we received support from PyBind 11 team at EPFL, I think, in Switzerland, and they provided a workaround for us to actually make it work. And we actually even now have MATLAB running as a part of our continuous integration workflow for PartMC. So whenever we change something in the project, it's actually tested if it still runs from MATLAB. Some of facts about this development, some of them may be fun facts, is that, let me stress that the whole concept of using C++ for interfacing Python and Fortran is strictly dependent on the fact that PartMC originally was coded in an object-oriented manner. So despite it was started 20 years ago, it's a very, very best practice example for modular object-oriented code, despite it's in Fortran. Something probably that was also not entirely expected at the beginning is that a big chunk of PyPartMC code base actually is written in CMake. So this static linkage and compilation of a dozen of packages in C, C++, and Fortran, this was a challenge. To make it run on Mac, Linux, Windows, most of the dependencies actually were not ready to use, and we were re-implementing the CMake compilation workflows for things like netcdf, for things like sundials, etc., to make it compatible with our assumption of static linkage. When we were happy with the static linkage working, we realized that actually it's against the Conda policy of package dissemination. So we cannot disseminate statically linked dependencies through Conda. So well, this stopped us from publishing a Conda package. It's still usable on Conda through pip, but we cannot publish on Conda due to static dependencies. We are still not able to automatically generate and disseminate universal binaries for the new Apple CPUs, essentially because G-Fortran doesn't still support cross-compilation for the universal binaries. It's a kind of surprising thing because there is so much Fortran code, for example, as a part of R code base, and it's still not obtainable with mainstream G-Fortran version. R guys release a custom version of G-Fortran for building R packages, but the problem is that it builds it, but they are unable to test it because there is a very little support for Apple Silicon in continuous integration platforms, at least not for free. So there are challenges. As I mentioned, the MATLAB bridge does have some issues. So there are a few workarounds that are documented in our README that need to be done before running it from MATLAB. But let me stress that we very highly appreciate the fact that MATLAB actually releases continuous integration machinery on GitHub that allows you to run arbitrary MATLAB code on GitHub without a license. So this is from the MATLAB MathWorks company behind MATLAB. and we can run MATLAB scripts, MATLAB plotting, MATLAB simulations on GitHub anonymously without any license, just using the MATLAB provided continuous integration actions. Let me also mention that the Software X journal experience was quite positive in the sense that actually the reviewers looked at the code, provided feedback for installation, and we needed to help the reviewers actually go through the installation, including Apple Silicon issues, before concluding the review. So just an experience from a new journal. And finally, there are some caveats, like the fact that propagation of exceptions from C++ through Fortran to C++, which we at first were happy to see that works. Later, we realized that actually it's a compiler-dependent, non-standard feature that makes the exception logic work essentially only when compiled with gfortran, not with other compilers. So there are some caveats. So last slide, a summary of what we hope we managed to enable by creating PyPartMC. Single command pip installation on 3 different operating systems that includes all dependencies. So this hopefully is an enabler for new users. We managed to use a modified PartMC codebase from also ecosystems and environments such as Julia, Matlab. And actually, what I have not highlighted, but what was implied, we also created C++ interface and C interface to PartMC. So this is just a byproduct, probably no one will ever use it. But if needed, there exists now a C and C++ interface to PartMC, which we needed to create in order to run PyBind 11 machinery on it. What is now enabled, and what is actually the case in one of another projects I maintain in PySDM, that PartMC can now be in a straightforward way used in test scenarios for other Python projects. This was something that wouldn't be possible without a lot of setting up and without going outside of Python ecosystem. Now, inside testing logic for other packages, we can compare against results from PartMC. Something that was realization we had later on, and this is maybe worth highlighting, is that besides Python having its advantages as a language, as a rich package ecosystem, etc., there is the packaging workflow through the pip command that handles dissemination of binary packages or source packages, compilation from source if a package is not available as a binary, selecting correct binary for different operating system, different hardware, but also actually there is something like mini-Linux, which is a Python way out of the glibc dependencies of different Linux versions. So probably some of you might have used a supercomputing environment where at some point one can see a message that some binary cannot be used because the version of C library is older or newer or incompatible, etc. And actually pip, because pip workflow and pip standard copes with it. So we have realized that Python being one thing, doing PyPartMC, we managed to disseminate binary versions of PartMC to many different hardware environments, many different software environments, including supercomputing platforms where people previously had trouble of getting all those dependencies working together. And from user perspective and also, for example, paper reviewer perspective, what we have achieved is the possibility to encapsulate simulation setup as well as input and output and analysis and plot within one single language file. So imagining a typical scenario of sending a paper for review with a PartMC simulation, instead of text files with input, a bash script with simulation logic, instructions for compiling PartMC, and Python scripts for simulation output. Now we have just one single language, possibly one single file. And what is probably not an advantage for every user, but could be for some potential users, is that we have the option of performing time stepping either from Fortran or from Python. Because we interface the internals of the package, not the outer API, we can do actually the time stepping from Python. And this enables us to couple the simulation that we create with external components that we could use every time step to either diagnose something or actually to change the attributes of particles. Think of chemistry, optics, or for example, coupling with fluid dynamics backend of a simulation. Finally, what was suggested by users as an advantage is that now generating ensembles of simulations, let's say you want to explore the, for example, for machine learning, you want to explore a multi-dimensional space of parameters, executing thousands of PartMC simulations. Now it's possible to be done within several loops in Python. Previously, each simulation would need to have at least 10 text files at the file system to be run. So from the point of view of generating thousands of simulations, this is a maintainability advantage. And finally, thanks to existence of platforms such as Colab or ARM Jupyter Hub, where we can execute notebooks and install Python packages, we are able to use PartMC in such platforms. Let me now go back to the simulation, and I'm happy to announce that we have a plot here with particle diameter on the x-axis and absorption efficiency on the y-axis, calculated with an external Python package for me scattering based on a PartMC simulation that was carried out on a freshly instantiated virtual machine anonymously in the cloud, which is also possible on ARM Jupyter Hub or Google Colab. So with this, let me almost conclude. I'm happy to share that ARM Research Highlights website also lists the package in the current state of the package with this impact point ability to run PartMC simulations in the cloud, including using the ARM Jupyter Hub. Let me acknowledge the funding from ASR, NSF, and Polish National Science Center, and let me thank you for your attention.
Okay, thank you so much for the talk, and yeah, I guess it's time for discussion or questions. And if anyone online has questions, you could put it in the chat or just unmute yourself. Let's see.
I'll ask a question if that's fine.
Oh yeah, go ahead.
Hey Sylwester, you answered my Conda question already, but I wanted to ask you about Mosaic. When I wanted to use Mosaic a few years ago, I had to like email the developers and get it from them, because I'm not sure if it was open source at that time. How did you navigate that with PartMC?
Mosaic is an optional dependency of PartMC for gas and particle chemistry. It's not open source. It's a closed source PNNL code base. It's usable with PyPartMC. If you have access to the code, you can compile it in, but it's not open, so we do not ship it with PyPartMC binaries. However, the group in Illinois came up with the alternative to Mosaic, which is being developed, and it's called CAMP. There's recent GMD paper describing the initial release of CAMP, and if I understand correctly, the goal is to provide at some point analogous functionality with an open source code base from CAMP. To be fair, both CAMP and Mosaic can be compiled with PyPartMC. So actually CAMP gets compiled into PyPartMC by default, but we do not have examples of how to use and analyze the data at this point. So there are no technical obstacles or challenges, but we have not developed examples that would depict use of CAMP with PyPartMC yet.
Okay, cool, great, thanks. Good to know about CAMP.
Thanks for the question.
So thanks for the talk. So you said it's like basically PartMC is a precompiled binary. So if there's like updates to or if you wanted to update PartMC, it would have to everything would have to be recompiled and then coupled to Python again, or?
So okay, so there I would say that there concerning updates there is the user perspective and the developer's perspective. So from user perspective, installation of PyPartMC implies a particular version of PartMC. So if we look at, I can try to maybe show it here. If we look at the GitHub repository of PyPartMC, and we go to this Git modules directory, you will see that each of the dependencies is pinned to a particular GitHub commit. So if you use PyPartMC version 1.2, it means that it is based on particular version of PartMC underneath, and it's exposed to the Python user with one of the version strings that you can access and ensure which version of the underlying library is used. So this is the user perspective. So the user cannot update PartMC without updating PyPartMC. This comes as a bundle, as a single file. From developer perspective, updating implies bumping the commit hash of any of these dependencies. And now one of the key features of this maybe somehow non-trivial and convoluted design with the C++ C layer with this IO layer is actually that if a new version of PartMC introduces some new input requirements, so that your input now must, for example, specify, I don't know, let's imagine initially you had 10 required species, now you have 12 required species. The advantage of this architecture is that it is only the version bump here that is needed without any modification to the C++ or C layer. Because what we provide, it's not a re-implementation of the input-output logic. We just provide re-implementation of the input-output API. So PartMC still thinks it uses its own text files by calling spec file read value. And we provide a C++ re-implementation of this read value, which takes values from Python session. So if PartMC requires new values to be provided, we just recompile with the new version and it works. It's not needed to add something to the C++ layer because PartMC uses a set of like read array, read value, read string, not read kappa. They use an abstraction layer for reading the input files, and we provide re-implementation of this IO layer and not of the whole input-output logic for PartMC. So maybe I made it a long answer, but the short answer is that the updates are relatively straightforward.
So this is really cool. I'm just wondering from the perspective of like transforming other legacy Fortran codes. From this process, do you think it requires a very specialized type of like pre-existing Fortran code? Like, is the fact that PartMC was very modular essential to making this pipeline possible?
Exactly. You phrased exactly one of the bottom lines here, that it was possible because the original code was engineered in a best practice manner with a lot of modularity, with a very, I would say, exemplary object orientation. So it's object orientation in the old Fortran, actually. So they do not use the Fortran 2008 or something like that. They use derived types. They pass pointers as these or self, etc. But there is this logic of object orientation is all around there. So it's straightforward to map it to C++ object orientation, Python object orientation, because all the methods require the intuitive arguments. So they require a self, they require an object which calls some method, etc. So mapping the internals to Python did not imply that we need to come up with some API. The API of PyPartMC is exactly the API of PartMC internals. So there were technological challenges to make it connect and run, but the API remains exactly as it is in the original code. So that's why we can use unmodified code, and that's why the whole project had these technical challenges, but it didn't imply that we need to change something in the original code. It was ready to be wrapped or interfaced with other object-oriented technologies like Julia, for example.
So if I want to have something similar to PyPartMC to run with my Fortran project, I would have to rewrite my Fortran project to modernize my own Fortran project first, so that it's object oriented and everything.
I cannot. It's impossible to answer because it's a very abstract question, and also the answer depends on your goal. Providing an interface to an outer layer of an API, like a few functions, would likely, for this, what we've just mentioned would not be really applicable. But if the aim is to provide access to internals of some Fortran code base to Python, then likely you might face the challenge of different assumptions in these languages. So Python, Julia, C++, Matlab, they assume that you have things that are initiated on resource acquisition, that can be allocated, deallocated, that there are no globals, that there are no common memory addresses, right? So there are some kind of very general language agnostic assumptions that could be easily violated if the Fortran code base is not engineered in a way that would actually envisage interfacing. But if it's just a matter of providing access to an outer layer, a few functions, many of these solutions work equally well. So it's not that it's hard to answer the question without knowing actual code base and actual use case, because it depends what kind of goal you want to achieve.
Hi, can I ask one more? It's maybe a little in the weeds, so I'd be happy to talk to Sylwester independently, if that's better.
You can go ahead, Robert.
Thanks. This is a lovely talk, and for me, it's quite timely because I have a broadband radiation code that I'm just getting Python front end for. We engineered for it from the beginning in the sense that there's a clear C API and all this stuff. We're not going to try and do the internals, but they're sort of computational kernels that we're trying to expose. You made a choice to go with pip, and I think it feels to me, you could correct me if I'm wrong, like that's what leads you to this sort of single binary, mono repo pinned versions approach, because the conda approach would maybe be to say, well, these things are you have to be these versions have to be compatible, right, one with another. So I wonder if that was if that was sort of a surprise for you, if you chose pip without a roughly speaking deep thought about how it would lead with this multi-language dependencies, or whether there was some philosophical thing you went in with your eyes wide open and you made that choice nonetheless.
So first of all, we definitely wanted to cater also to non-conda community. So pip, in a way, I would say, is more general than conda. So you can use pip from conda, but users without conda would potentially struggle having a package which relies on dependencies that are not easily installable. And the key technological challenge that is behind this static linkage is actually the lack of Fortran API. So Fortran modules, Fortran dependencies need to be compiled with the same compiler as a binary that loads them and uses. So even the G-Fortran version makes, for example, netcdf library incompatible with a version that comes from a new compiler. Indeed, conda addresses it by providing all the compilation tools in a single environment. So indeed, assuming that we want to start with conda, all the static linkage would be inappropriate according to conda guidelines, and would not be needed. Our starting point was that we want to go for as broad audience as possible. So, for example, a very typical end user for us is someone who opens a freshly purchased MacBook, where Python is already installed, while conda is not. So we wanted to make it usable by just writing pip install. Second, we wanted it to run on Colab, ARM, Jupyter Hub, etc. And to my understanding, some of the dependencies, some of the C++, Fortran dependencies would be tricky to obtain on platforms such as Colab. While if we do pip install and we disseminate the binaries as a single file with all dependencies with statically linked in, this is possible. So clearly there are many paths, and it very much depends on the end user you are thinking about when doing the design decision. So with our fresh MacBook user, Colab user, ARM Jupyter Hub user as potential end users, we went with this idea of not depending on conda, but clearly conda does address the challenges that led us to the static linkage in an alternative way, which is essentially a more elegant way, because it's better to provide a consistent shared library ecosystem than to ship very fat binaries with 15 libraries statically linked in. So yeah, it depends on, I guess, on the end user figure we start with.
So that's a very informative answer. Thank you.
Thank you for the question.
So thank you so much, but in the interest of time, I'm just gonna end the session here, and then maybe we can continue the discussion here in person over lunch.
Thank you for joining and for the
Thanks
opportunity.
everyone on Zoom.
Thank you.